video lecture series on operating systems. In last video, we have started second unit and we have seen about the concepts like what is the process concepts, and we have seen about the process state diagram and the process control block. In today's session, we are going to see about process scheduling, what are the scheduling queues, schedulers and context switching. Now coming to the process scheduling, in a multi-programming environment, in order to allocate different multiple processes which are appearing into the CPU, it is necessary for an operating system to check and to decide which process have to be allocated to CPU for execution. So the process scheduling is one of the operating system tasks that will schedule a process in the CPU for execution. So whichever the state a process may be, whether it is either it is in running state or ready state or waiting state, such processes are scheduled towards the CPU for execution by using the process scheduling. This process scheduling will allow the operating system in order to allocate the time interval of CPU for execution of the process. So the main goal of this process scheduling is it always keeps the CPU busy. That is, whenever a process executes and then goes out for IO operation or some interruption, due to these interruptions, if a process comes out of CPU from its execution, immediately this process scheduling will take care of assigning the next process which has to be allocated to the CPU. And coming to the topic scheduling queues. So in order to allocate a process for a CPU, in order to execute it, there are different kinds of queues. So say for example, a process may be in different states while executing. Okay, like we have seen the 5 states: ready, running, waiting, and new state and terminated state. So whatever the state it is, these process scheduling queues will help the operating system to maintain each process in a separate queue. Based on the state in which the process is present, this operating system will place the queue in that process in that particular queue. Okay, so each and every process state is stored in the process control block, and that state is taken by the operating system, and based on that state, each process is placed in a particular queue. So all the processes, when there are multiple processes to be executed at CPU, all the processes which are present for execution, so based on their state, those processes which are in the same state are placed in the same queue. Okay, and therefore, whenever the state of a process is modified, that is, if it is moved from ready state to running state, all the processes which are in the ready state, when they move to the running state, the queue also will be changed for that particular process. So now let us see what are the queues, different types of scheduling queues available for us. So we have 3 types of scheduling queues, in which the first is the job queue. So the job queue, in the sense, as soon as a process is loaded into the main memory. See, right from the starting of our lecture series, we are discussing that in order to execute a process, that should be loaded into the main memory from the secondary memory first. So as soon as a process is loaded into main memory, it is said to be in new state. So those processes which are in new state are placed in the job queue. Okay, so after putting the process into the main memory, the process will be allocated all the required resources. So from that point, when the process is ready with all the resources it needs, the process is said to be in ready state. That is, when the resources are allocated, the process moves from new to ready state. So whenever a process moves to the ready state, all those processes which are present in ready state are placed in the ready queue. That is the second type of queue we have. So all the processes which are ready with their resources are placed in the ready queue. Whereas during the execution, so after a process is in ready state, it indicates the process is ready for execution. So the a process is ready with all its resources, it will be moved to the CPU for execution. That is when so that process which is present in CPU for execution is said to be in running state. So during execution, if at all, if a process want to take some input, or if it want to print some output, or if there is any interruption for that process, the process may come out of the CPU for execution. So in that case, when a process comes out of the CPU for execution, a process is said to be in waiting state. So those processes which are present in waiting state may have different reasons to be in that waiting state. So if a process comes out from the CPU and placed in a waiting state due to some IO event, then that process can be placed in the IO queue. So that is, you can see the third type as the device queue. There are number of device queues present based upon the requirement why a process comes out of the CPU. If it comes out of the CPU due to IO operation, then we can say that the operating system will place that process into the IO queue. If a process comes out from the CPU due to some interruption, then it may be placed in the interrupt queue. So you can observe the queuing diagram of a process while it is being executed. So here you can see the ready queue in which resources with all the required resources, the process with all the required resources are placed in the ready queue. So once a process is ready with all the requirements, it is moved to the CPU for execution. So while executing, there may be four reasons for a process to come out of the CPU. So first is the IO request. So if it have any IO request to execute, in that case the process comes out of the CPU and it will be placed in the IO queue. So once the process is done with its service, that is taking input or producing the output, then after taking, say for example, if it is taking input, after taking the input, the process can be placed in the ready queue for again resuming its execution. If it comes out, if you are using a time sharing operating systems, a process may come out of the CPU due to the expiration of its time slot. So if at all the time slot is expired, the process may be taken out of the CPU and then placed in the ready queue again. Then third is forking a child. That is, once if a new process is created due to the execution of a process, then that new process is called a child process, and due to which this new process has been created, that original process is called the parent process. So in that case, in order to create a new child process, the operating system will use a system called fork. So when forking a new child process, the parent process have to wait until the child has been completed its execution. So until the child completes its execution, the process have to wait, and then after the child has completed its execution, the parent process is again moved to the ready queue. And the last case when a process will come out is if an interrupt has occurred. So if the interrupt has occurred, the process have to come out from the CPU. It have to wait until the interrupt has been executed and then move to the ready queue for resuming its execution. So this is about the queuing diagram of process scheduling. And then we have here you can see the three situations where a process can come out. Okay, so a process could issue an IO request. Then if there is an IO request, a process may come out. If there is a new child process, a process may come out of the CPU, and if there is an interrupt, then the process may forcibly, that is, wantedly be removed from the CPU. And then you can see in the first two cases of the above slide, that is when a fourth child is, when a child process is created, as well as the first two cases, you can see the process will keep on be switching from the ready state to running state, and running state to the waiting state, and to ready state again. That is, all the all the three stages, the process will be moving to all these three states in a cyclic format. And this cycle will continue until the process terminates completely. And then this is about the scheduling queues. So coming to the schedulers, a scheduler is a type of system software that will allow you to handle the process scheduling. So we are telling a process will be moved to CPU, and whenever this process have some IO request, this process have to move out from the CPU, and other process have to be allocated to the CPU for execution. Then how a operating system will know which process has to be allocated to CPU first? So for that purpose, we have scheduling algorithms. So these scheduling algorithms will decide which process have to be allocated CPU first. So before this scheduling algorithms execute, there is one more concept called scheduler, which is responsible for executing the scheduling algorithms. So this allows the scheduling algorithms to schedule a process into CPU for execution. Okay, when a process migrates among various scheduling queues throughout its lifetime. So throughout its execution, the process will be moving about all these scheduling queues. Okay, so this operating system will select the processes that are present in the scheduling queues, and this scheduler will select the processes that are present in the scheduling queues and allocate them to the CPU. So coming to the types of schedulers, we have three types of schedulers. One is long-term, short-term, and medium-term schedulers. So long-term scheduler is used in the environment of batch operating systems. So it is also called a job scheduler, because if you observe in batch operating systems, each and every data collected from the user is considered as a job. And so the long-term scheduler is called a job scheduler. So this long-term scheduler in an operating system like batch operating system, this long-term scheduler will collect all the jobs submitted by the user and store it in some memory. So store all the pool of data in some memory. Later on, when the time comes for execution, this job scheduler will collect the pool of data from the memory and then send it to the CPU for execution. Okay, so then comes for your short-term scheduler. The short-term scheduler is also known as the CPU scheduler. This CPU scheduler will execute whenever the program comes out for an IO request or an interrupt. Okay, so in the case of the multi-programming environment, this short-term scheduler will be executed. This helps you from a group of available process for execution. The short-term scheduler will help you that to select the processes that are ready for execution. Okay, and the dispatcher is a program which sends the selected process to the CPU for execution. So this dispatcher will control the CPU, will control the process present at the CPU that are selected by the short-term scheduler. Then let us see the difference between these two schedulers. So when the main difference that is regarding this long-term and short-term scheduler is in their frequency of execution. So if you observe, a short-term scheduler will be executed frequently within a few milliseconds. So this scheduler will be executed very fast. Okay, and then a process may execute, if you consider a CPU is capable of executing millions of instructions in a second. So in that case, a process can be executed in CPU only for a few milliseconds. Okay, and before it comes out of the CPU for an IO request, a process may execute only for a few milliseconds. So when the process comes out of the CPU for after executing for few milliseconds, the short-term scheduler will activate and decide which is the next process to be allocated for the CPU. Say for example, if your process have been executed for 100 milliseconds before it comes out for the IO request. So when it comes out for the IO request, let us consider your short-term scheduler will take a 10 seconds of time in order to decide what is the next process to be allocated to the CPU. Now in that case, for a process to execute for 100 milliseconds and plus 10 seconds for deciding what is the next process to be allocated. So on an average, if you calculate, the CPU time will be wasted 9%. The 9% of a CPU's time will be wasted in order to only decide what is the next process to be allocated to the CPU. Okay, and coming to the long-term scheduler, if you see, the long-term scheduler may execute for frequently between minutes or seconds, because it should collect all the data from the different users. It should collect all the jobs from different users. So this long-term scheduler will control the degree of multi-programming. So what is this degree of multi-programming? The number of processes that are being created with the number of processes that are completing their execution will come under the degree of multiprocessing. So this long-term scheduler will control the degree of multiprogramming. So say for example, if your degree of multiprogramming is stable in the sense the number of processes that are created are equal to the number of processes that are being terminated or that are completing their execution. That is, process creation rate is equal to the process departure rate. Then the the degree of multiprogramming is said to be stable. Then if the multiprogramming degree is stable, then the long-term scheduler may need to be invoked only when a process is terminated. So only whenever a process is leaving from the system, the long-term scheduler will be invoked, and then it will select the next process for execution in the CPU. Okay, so that the long-term scheduler can afford, or it can take more time when compared to the short-term scheduler in order to decide what process have to be allocated to the CPU. So see, these processes can be decided as two types. One is the IO bound process and the other is a CPU bound process. In case of IO bound process, if your process is having more number of IO requests, say for example, if you have 30 instructions, out of which 20 are the IO instructions and 10 are the computational instructions, then your process is said to be a IO bound process. A process with more number of input-output operations is called IO bound process. And then coming to the CPU bound process, a process with less number of IO instructions and more computational instructions, more number of calculations. If you include more number of calculations within your program, then that process is called CPU bound process. Then the CPU bound process need not leave the CPU frequently in order to take the IO request. Okay. Then coming to this long-term scheduler, this long-term scheduler should have a good process mix. That is, it should not select all the completely IO bound process to send to the CPU, or it should not select all the CPU bound process to send to the CPU. It should mix the process available. So say for example, if it selects IO bound process now, then the next process to be selected should be the CPU bound process. This is required because if it selects all the IO bound process, all the process that have many IO requests will be residing in the IO queue. Okay, if it selects all the CPU bound process, all the CPU process will be present, all the process will be present in the ready queue in order to enter the CPU, and then the IO queue will be empty. So in order to reduce this problem, the long-term scheduler should make use of a good mix of CPU and IO bound process. And then we have the third scheduler, medium-term scheduler. So the medium-term scheduler is mainly used for the swapped out process. So these swapped out process are those which are coming out of the CPU before their termination, before their complete termination. So why a process will come out of the CPU before its termination? Because it may have an IO request, or then an interrupt may be occurred in order to continue its execution. So those processes which are having such interrupts are swapped out of the CPU. Say for example, a process is swapped out of the CPU for IO request. So after completing its IO request, now the process is ready to enter into the CPU. And at the same time, if there are process P2, P3 and P4 for your CPU in order to execute, so which process should the scheduler select? Either the process which is ready for its resumption or the new process which are present in the main memory. So what is the decision to be made? So for that purpose, the medium term scheduler will collect all the processes which are ready with their resources, which are swapped out due to some interruption, and which are ready with the resources, and the medium term scheduler will place all these processes in a queue. So this queue is merged with the ready queue, and it will send this suspended process or the swapped out process into the CPU for execution. So including this medium term scheduler, in the above previously seen queuing diagram, you can modify the queuing diagram as follows. So you can see previously we have seen 4 reasons for a process to come out from the CPU. So now if you see all the processes which are coming out of the CPU due to some interruption are placed in a ready queue. All those which are partially executed are placed in the ready queue. So they are placed in the separate queue by the medium term scheduler. Then these processes are moved to the ready queue for execution of CPU. Execution at CPU. Okay. And that is about the middle term scheduling. So middle term scheduler. And then the last concept we have is the context switch. So whenever a process wants to come out from the CPU before completing its execution, the kernel will save the contents of its process control block with the operating system files. So that saving is known as a state save, and then it allocates the next process for the CPU. So before allocating the next process for the CPU, all the contents of that next process will be loaded into the kernel. Okay, so this is called state reload. So once this process, the second process have been completed, again the process which is suspended previously will be moved to the CPU. So before moving this suspended process into the CPU, the kernel will again restore the saved contents of this suspended process into the CPU again. And this restoration of the saved contents of the process control block of the suspended process is known as the state restore. This state save and state restore of the contents of the process control block of different process between the CPU and the kernel is known as the context switch. So you can observe this in the following diagram. So here we have two processes, P1 and P0 and P1. And if you observe, while the time the say for example, if you observe the time, so if you observe here, the time where the process P0 has stopped its execution, all the contents of its process control block are moved to the all the present data of this process control block are moved to the or saved by the kernel. So once the state save is completed for the process P0, the operating system or the kernel will try to restore the contents of the process P1 into the kernel. So once the state of the process P1 is loaded, then the process P1 will be executing. So if at this point of time, if the process P1 needs some IO request or some interruption, then the process P1 will come out of the CPU by having its state saved on the or the details of its process control block, and then the operating system or the kernel will try to restore the contents of the process control block where the contents of are saved previously are again restored. So after restoring, the process P0 will start its execution. Okay, so this is the context switch. This saving of the data and then restoring the same data when again the process is being executed is known as the context switch. So thank you is known as the context switch. This is regarding your schedulers and the context switch. Watching this video. In next video, we'll be learning about the operations on process.